Let's take a look at the math associated with the drag force. By the time you're done with this, you ought to be able to solve any first-order differential equation there is by my favorite expedient of knowing the answer in advance and writing it down with the good old-fashioned sit-and-stare method, plus or minus a few of those handy little graphical transformations, move the function up, move the function over, flip the function around, that you learned in Algebra 2 Trig. Let's get started. We're looking at an object in the air on its way down, such that it's got the force of gravity going down and an ever-increasing drag force going up. We're choosing down as positive in this case, and we know that the terminal velocity will eventually be reached when the drag force, model 1, linear dependence, drag force equals BV going opposite to your direction of motion, is equal to your weight. We're looking at a problem that will eventually terminate in a terminal velocity of mg over b as shown. Long term, this is where we're going. Let's use that knowledge to figure out what happens to your velocity in the air in the short term. What's going on with motion under this kind of air drag? First and foremost, we know the initial velocity. The initial velocity is clearly 0. Either the object, whatsoever it was dropped from rest and experienced some small amount of air drag on its way down, or it went up first, turned around at a velocity of 0, and started its downward trip. They've got you coming and going. For some reason, if you started with rocket boosters, we'll simply put initial velocity 0 further left on the axis over here before you turned your rocket boosters on. There's no other way around it. Eventually, you'll get dropped. You will fall and fall and fall and fall. Your speed will increase, and we know what the end of the problem is. Let's do this by our favorite method of knowing the answer in advance. Do all the easy parts first, and then worry about the hard parts. We are looking at velocity that we know is going to come to an asymptote sooner or later. A final value of terminal speed mg over b. Long term, this is where we're going. We might as well ensure that we get there. There we are. There is our terminal velocity. Now we just have to connect the dots between here and there. The second thing we know is that air drag takes a long time to build up. If you drop something, originally it's going to accelerate at 9.81 meters per second. And on a velocity time graph, that's the slope. Initially, for some period of time, we know that the slope is going to be a constant. It's going to be a constant 9.81. At this stage of the motion, there is no difference between the motion with air drag that we're graphing and simple free fall. Free fall will continue picking up speed at 9.81 meters per second squared until you hit the ground. However, in the real world, where there is air drag that's going to come into play sooner or later, our drag force is not going to pick up this much speed. It's got to go from here to there in a nice, continuous function. Now we connect the dots, make sure we've achieved continuity, and there is the solution to our problem. This is what's going to happen to our velocity with air drag. When we can fit an equation to this curve, we'll be done and we'll have our answer. Let's start with the shape. It has one, and only one, nice flat asymptote over here on the right. And the only function I know of that has precisely one horizontal asymptote is exponential growth and or decay. Let's check it out. Exponential growth has the asymptote we're looking for over here on the left. There it is. It's nice and flat. We want our exponent on the right, which means our next stop is going to be exponential decay. There it is. It decays, it decays down. We don't want to go down. We want to go up. We want to flip this graph over the x-axis. How do we do that? Last time I checked, We flipped it over the x-axis. This way. There we go. That's the shape we want. That's the shape we want. All right. The shape we want is kind of low down. I know how to fix that. There we go. Now we just need to shift this upward by the right amount. So let's see. Oh, hey, we got it. We got it. It goes right through 0, 0, like we wanted. How do we do that? Well, thank you very much, Desmos.com, for giving random values to our constants. It looks like this goes through 0, 0 when C at the end and A at the beginning are exactly the same number. So why have two variables when you could have one? Get rid of that. We are in good shape. Now, please notice that we can factor out a common value of A here, and if we're getting to our asymptote way too early, we can put in a rate of change. We can increase the rate of change, or we can slow down the rate of change and get there much more slowly. There we go. That looks about right. We're looking at a leading coefficient and a function of twice flipped exponential decay, and we're looking at it to model velocity and time. Our velocity is going to depend on something. It's going to have a rate of change over time. Now check this out. When time equals 0, e to the 0 is 1, 1 minus 1 is 0, we're in good shape. This is what we'll call a boundary condition, or a boundary value condition. Here is our first condition. We needed to go through 0, 0 right here. We have achieved our first boundary condition by the cunning flipping of our shape. Our second boundary condition is after a long, long, long time. Technically, we'll never get there, says math class. Yeah, close enough for government work, says physics. After a long time, we should level off at our terminal velocity. E to the negative infinity is 1 over e to the infinity. That's 1 over a ridiculously huge number. That is, for all practical purposes, approaching 0. It's going to leave 1. 1 what? One of these. This is our initial value, and this is how we satisfy the condition. By the simple expedient of sit and stare, we've already gotten as far as velocity as a function of time approaches the terminal velocity at an exponentially flipped decaying rate over time. We are down to guess and check for what's going to control the rate of change. I'm looking at M, I'm looking at B, I'm looking at G. They're all knocking around here. And if we don't want to bother with guess and check, notice that we know what VT is. And we know another thing. We know the force, we know the mass. That means we know the acceleration. We know the acceleration, which is the first derivative of our nice, tidy little equation here. And we know that the acceleration in the downward direction starts at g, and as the speed builds up, is opposed by the drag force divided by mass, because the last time I checked, force was mass times acceleration. Now, take the derivative of this pupster and solve for r. Pause the video, plus play to check your work. Let's expand this to make sure we can take the derivative clearly. Boom, it's a constant, time derivative of 0. Hey, look, exponential function. I love exponential functions. The derivative is itself, only chain rule multiplied by negative r. So we have r times our original function and that's going to be equal to the acceleration. Now, if it were calculus class, I would finish this problem, but watch. Bam. First thing we want here is a g. We have r times m over b times g. I believe we were going to guess and check. I believe my first guess for r is going to be b over m, to knock this out, and leave a g out front. Let's try it and see. We were only after r anyway. We weren't after some kind of calculus proof. This is going to be a long one to explain, given that this b is this one up here with the leading coefficient. Do not forget that. And all this other stuff we have carrying around that we're now guessing looks like this. Is it true that this side is going to be the same as this side? Yeah, switch the variables, I know. I'm hoping they will all cancel out in the end, and it will not matter. Watch this. Cancel, 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 cancel. G minus G goes cancel. Minus minus equals plus. And there we have it. B over M, cancel, cancel. And there is everything we need. We are left with this G, e to the negative B over MT. Booyah! Got it on the first try. Fit, connect the dots, guess, and check. We have a final equation for velocity under air drag. Starting from rest, picking up speed until you get to a terminal velocity, it is going to be that terminal velocity, whatsoever it is, mg over b in our case, growing by a flipped, exponentially decaying rate of b over m over time. And done. Recognizing this answer off the graph is going to get you minimum of 11 out of 15 on your AP question. Being able to document your work like this, step by step, with some form of calculus, is worth the last 4 points for a perfect score. All this by guess and check. Takeaway conclusion. Drag force is a differential equation. Up here, we kind of camouflaged it. Take a look. You have a derivative that depends on itself. This is a first-order differential equation where the derivative of v depends on v. Or to write it properly as a differential equation, the derivative of v is itself the original v, only multiplied by a constant out front of negative b over m. Differential equations are done by pattern recognition. You see one, you see them all. Name me a function whose first derivative is itself. Go. Done. That's what I thought. It's either a flat zero of nothing, or it's exponential growth or decay. I'll give you one guess as to which one this is going to be. Yeah, that's right. It's got a big honking negative out front. Why? Because when you take the derivative of a negative, that negative here is going to come out front there. If you see any first-order differential equation here on after that is a positive number times itself, that is exponential growth. If you see any first-order differential equation that is negative, that is exponential decay. Everything else is throwing it up on a graph and whacking the constant out front until it fits with the numbers given in your scenario, and whacking the rate of change until, bless my soul, we don't need to whack it at all. Look, it's the coefficient right here in our differential equation. Bam, plug, solve, rate of change. This isn't some random guessy number at all. It's the coefficient of the original equation. Ladies and gentlemen, first-order differential equations, everyone you will ever see in less than 15 minutes.